It's like room temperature. So it needs to be cold. So that's why you have this really big sun shield that's protecting it from the sun. So this side will always be facing the sun, and this side will always be facing away from the sun. And maybe the first impression also when looking at this is how scary it is that you just have this exposed mirror out in space, right? There's probably these micrometeoroids that can come in and hit us. There's already evidence that that's been happening. There's one micrometeoroid that was a little bit bigger than they expected, which is a little scary. But they did the calculation, they should be okay. But this is kind of a very unique design for a telescope, having this mirror just exposed out there. Yeah, and all the instruments are kind of behind the mirror here. Light comes in, hits the mirror, hits the secondary, goes back in to the instrument module, and that's where all the optical stuff gets done. You have the spacecraft bus on the other side, you know, solar panels, communications, that sort of stuff. There you go. So yeah, on one side, negative 390 degrees Fahrenheit. On the other side, 260 degrees. So quite a ridiculous temperature difference. And the reason it's taking so long for this telescope to get up is all this new technology that's never been tested before. So this sun shield, this whole idea of this sun shield and having such a big temperature differential, that's all new. And so that's why it took so long. That's why it's been so expensive. But it's all this new technology that it's working right now.
How large is it? What's the scale?
Yeah, it's a good question. So the kind of analogy everybody puts out is the size of a tennis court. So the mirror here is 6.4 meters, so much taller than I am, right? But the sun shield itself would take up most of a tennis court. It's a pretty big, yeah. Yeah.
Are we constrained to only look at things that are 90 degrees away from the sun?
Yeah, so it's not necessarily directly 90 degrees, but you just, yeah, you always have to have this thing, you know, the actual telescope away from the sun. But then there's this, the telescope can then, if I'm the sun, here's the sun shield, James Webb can then be any kind of 30, 360 degrees. So there's, it's called, they call it the field of regard. And so there's this strip along the sky that the telescope can look at any given time. And so that's it's a constraint when you look, when you are planning these observations, is you can only see an object, you know, twice a year when it crosses that field of regard. So yeah, it's kind of a weird. So like I said, it's a big mirror, 6.4 meters. You can compare that to Hubble's. Hubble's about the size of a person, right? 2.4 meters. It's aluminum coated, so it looks like, you know, your bathroom mirror. It's much fancier than that, but it's coated with aluminum. So that's because it's an optical telescope, right? Just like your bathroom mirror is an optical mirror, Hubble is an optical telescope. Now, Webb is different. It's an infrared telescope. Turns out gold is very reflecting for infrared light, and so it's gold coated. So it's got what, 50 atoms thick of gold coated on top of it. The mirrors themselves are beryllium because beryllium is really strong at these really cold temperatures. And the beryllium turns out was mined in Utah, which is kind of cool. So that's Utah's connection to the telescope, is that the actual structure of the mirror is mined.
6.4 meters is a little over 21 feet.
Okay, wow, yeah. It's I think I did the math right before this, 7.1 times the light collecting area of Hubble. It's pretty impressive, right? The whole thing had to be folded up too. There's no rocket fairing that would fit this whole thing in. So I had to unfold and everything. Just a whole nother story. Yeah.
Where is this satellite? Where is the mirror? Anyway,
The telescope?
where is it located?
So it's out in L2.
Oh, the L2 point is 1,000,000+ miles. out.
Yeah, so it's a little bit past the moon there. That's like 3 times farther. A lot past the moon, yeah. It's where the gravity of the Earth and the sun is balanced such that it can orbit along with us. So its orbital period is 1 year, just like we are. So it's orbiting with us, even though it's a little bit further past us. And that's to keep it in like a nice isolated environment where it can look at whatever it wants without the Earth or the moon getting in the way. Meanwhile, Hubble is in low Earth orbit. So it's orbiting the Earth, and so it gets eclipsed by the Earth every 90 or every 45 minutes. So that's a pain. So Hubble can just stare at blank fields of space for hours and hours and hours, which is exactly what it's designed to do. Yeah.
That's what I was going to ask about. I don't think Webb has the opportunity to stare at a single space for 2 weeks in length. Just how fast or how much faster are the cameras as referred to the wavelengths that it's capturing on Webb as opposed to Hubble?
As opposed to Hubble, yeah, that's a good question. I don't have like good numbers, but 7.1 times the light collecting area, and it's all of the instruments are. There's a whole bunch of technology that's been gone into making things more efficient, making optical coding of the instruments more efficient and everything. And yeah, like it's designed to be making these deep fields and looking at these really deep, far away galaxies that are far away. Okay, more questions than I can. Yeah.
Okay, so if Webb is moving around our sun along with us, it's moving very fast, right? Okay,
International
so
distance.
how does it take a picture of something billions of light years away on time, at time exposure? How do you do that when the camera's moving?
I think it's all about the relative distance that the thing's really far away. So the angle at which it's going around the sun, right? But the angle at which it has to move itself to keep pointing at the object is really tiny, just because everything's so far away. So it's able to, it's moving fast in a human sense, but in astronomical sense, though, it's able to just stare.
Okay.
It's also orbiting like this,
Yeah.
not orbiting like this. That makes sense.
Oh, really?
So it's, I mean, it's great.
It has gyroscopes, so it stays pointed in the same place until you try to.
And it's actually got an instrument to do just that. So these are the 4 instruments on JWST. One of them, FGS/NIRS. FGS stands for the Fine Guidance Sensor. So it's basically a camera that's just looking at where the telescope's looking, taking pictures to keep it aligned as it's moving around.
There was even a test where they were trying to track meteoroid or something like that. They were expecting only 30 meters per second. They were tracking a close object. They were able to track it like 60 meters per second.
Yeah. So like the telescope wasn't meant to be able to track asteroids or solar system objects. There's some requirements that it has to be able to do a little bit of that. But indeed, yeah, it appears that it's better at doing that than they thought it was. So there's going to be faster asteroids that's going to be able to track, which is good news. Is there another question real quick? Yeah.
Well, it's my understanding it orbits the L2 point.
Yeah, it's in a halo orbit there.
Yeah, how large is the radius of that orbit?
That's a good question. At the very end, I have probably a figure that's not to scale. I have a good. It's huge. It's probably pretty big. That's why it needs thrusters to keep it in that halo orbit. And that was the main kind of worry, or the limiting factor in the lifetime of the telescope, was how much fuel it would have to keep itself in that halo orbit around the L2 point. Turns out that ESA was really good at its launch, and so what was going to be 5 years worth of fuel has turned into more than 20.
It's competing, right? There's another thing there at L2. So
Yeah, there's a bunch of
reasons
things
the halos from hitting the other things.
Yeah, there's a bunch of things at L2 now. There's Planck out there. There's a few others, but it's such a big area that I don't think that's
Space is mostly empty space.
So like I mentioned, telescope is looking at the infrared. Infrared is like heat. So you're giving off, I think you're giving off light that peaks at about 10 microns, which is right in the James Webb's sweet spot. So it's meant to look at things that are about things giving off heat, as opposed to the optical, which like Hubble would take a picture like this. JWST would take a picture. Here's where it kind of stacks up in terms of the electromagnetic spectrum. So going from short wavelengths to long wavelengths, you got Hubble, which only goes out to about 2.5 microns or 2,500 nanometers. So it's well into the near infrared. But JWST picks up and goes from about half a micron all the way out to 28.8 microns, which kind of fills the gap here with Spitzer Space Telescope, which is maybe more analogous as JWST's predecessor. This is a previous infrared telescope. It was only 0.6 meters in size, its mirror. So it, looked at a lot of the same things that JWST is going to look at, but at much lower resolution spatially and speed. Okay, so why infrared? This is a good figure to show, invisible, you look up, it's like the disk of the galaxy and you see these beautiful clouds, but sometimes you want to see through the clouds. So if you look at longer wavelength light, you can look through some of those clouds and just look at all the details you can see. You can look through some of these gas clouds. You can pick up light from cooler stars as well. And so there's just a whole nother world that opens up the near infrared. And then the mid infrared, as I'm talking about with stuff giving off heat, some of that really cold gas, you can then kind of detect its own thermal emission, and you can then trace that gas a lot better than you could in the visible. So it's this kind of whole new universe that opens up in the near. See, I don't want to get too much time. So yeah, the telescope is built to look at really distant galaxies. That's why it's looking in the infrared. And as you know, the universe is expanding. So the universe is redshifted. Or the further away you look at a galaxy, the more redshifted it's going to be, which means that the most distant galaxies are going to be the brightest at infrared wavelengths. This is a telescope built to look at those really dim, really redshifted galaxies that are, only hundreds of millions of years after the Big Bang. Kind of gave it away. So how far do you think the telescope will look back into the past? D, that's right, yeah. 13.5 billion years. If the universe is 13.85 billion years, JWST is going to look only a few hundred million years after that, at those very first galaxies, those very first stars that formed. Okay, so let's actually look at what the telescope's been up to, and for that to get started, I'll hand off to Joe, who knows way more about galaxies than I.
So maybe we should do the PhD level question. How far away can James Webb look if it can look back 13.5 billion years?
25 light years.
Wrong.
45.
40, yeah, it's close to 40 billion light years away. You say, wait a minute, what are you talking about? How can that be? The universe has expanded so much in the time between the time when the light left that galaxy and now. What would be 13.5 billion light years has been stretched to over 40 billion light years now, today. So we're really looking a long, long distance into space when you talk about looking back in time. And that can get really confusing when we talk about looking back in time versus looking far away in space. But for astronomers, a telescope is a time machine. And so when you look at any object, you're also seeing not just far away, but you're seeing backwards in time. You're seeing an object as it was at a time in the past. So this is where the language gets a little confusing with PR press releases and things you might see in the news. When they say we're looking at the oldest galaxies in the universe, but we're seeing them when they're very young, you can see how that could be confusing. What we're doing is we're seeing what would be old today, if we could see it today, at a time when it's very young. So we're actually looking at the baby pictures of galaxies that are quite old today. So this is one of the first pictures that they took, or that they released last month. And I think what we wanted to talk about today as much as anything is what you can see in these pictures. Why are they such a big deal? And for me, the most important thing about these pictures that they released over the last month is just that these are the first of thousands of pictures just like them that are going to be released, and spectra that are going to be released over the next, hopefully, 20 years. Well, into my retirement, definitely. But this particular picture is one of the first they released. It's a kind of a deep field image. It's not as deep as they will eventually do, I'm sure. But it has a number of really interesting features to it that I'd like to talk about scientifically. The first thing is that there's a super bright star right there. This, to an astronomer who has commissioned a telescope, that's the obvious thing you want to do. You want to make sure whatever you target has some good bright stars in it so that you have a reference for your alignment, for your image quality testing that you can get in very short exposures. You'll notice that the Hubble deep field that they did when the telescope was mature doesn't have any bright stars in it. This one, they intentionally picked a cluster of galaxies that's close to a bright star, so they have a reference. That's neither here nor there, but that's why, I'm sure that's why they did it there. Now we have a cluster of galaxies here, so that's interesting. Galaxy clusters are a test bed for all kinds of theories about stellar evolution and galaxy evolution. We have a bunch of these arcs around here, which are gravitational lens arcs. And then in the background, there are all these little faint fuzzy things. So this is a very, very rich image. The main thing that James Webb provides, aside from this 7 times bigger aperture, is thousands of times more pixels than Hubble has at any given time. There's just so much more data because the cameras are so much bigger. So this is just a kind of introduction to galaxy clusters. A typical small group or cluster might have 50 galaxies like our local group. It might have a total mass of about 3 times 10 to the 13 solar masses, and most of that being dark matter. This thing right here, mass to light ratio, tells you basically how much dark matter there is in a cluster. And in the hundreds means that the luminous matter just represents a tiny fraction of the total mass. But a rich cluster could have over 1,000 numbers, 1,000 galactic numbers, each with trillions of stars in them, or at least hundreds of billions of stars. Typically 100 times more mass, and a mass to light ratio that's now even more extreme. So the bigger the cluster, the bigger the mass congregation in the universe, the more dark matter it has as a fraction. So dark matter is really what dominates the dynamics of the universe and the stars in the universe. So here's a typical cluster. This is a ground-based image of a nearby cluster. And you can see it has a few big, bright, massive elliptical galaxies towards the center, and then lots of smaller ones. And one thing you'll notice about clusters is they have very few spiral galaxies, a few disk galaxies, but that one is arguably part of the Coronary cluster, and it's really the only big, giant spiral you see close to the center. This is the Coma cluster. Oh, by the way, if you happen to live in the southern hemisphere, this would be just as easy target with all those Virgo galaxies that we look at in the spring. So comparable in distance to Virgo. This is about 5 times farther away than that. The Coma cluster is the nearest big rich cluster that we can see. And now you can see something that has closer to 1,000 galaxies or more. All of these faint things are all galaxy cluster members in the Coma cluster. And how many spiral galaxies do you see? Got like 5. Not many. Elliptical galaxies congregate towards the most massive, dense regions. They're the oldest galaxies. They're the most massive galaxies. They formed first. So here's another cluster. This is Abell 370 with the Hubble Space Telescope now. And as you get closer or higher resolution images, you start to see some funny things popping out. These little arcs. Those are background galaxies that are being gravitationally lensed by the mass of the cluster itself. They're not part of this cluster. They're in the distant background. And you can see right away that they have strikingly different colors. Generally speaking, the galaxy cluster members are typically in the optical. This is an optical image now from Space Telescope, are typically orange or yellow. And a lot of these things are quite blue. I want you to remember those colors. Cluster galaxies orange, arcs are blue. Here's another galaxy cluster, even a more massive, rich cluster. And you can see again that this arc, this pattern of gravitational lensing tends to form arcs around there. If we zoom in on that a little closer, you can see that there's just hundreds of these little arcs. These are background lens galaxies. So how does that work? Gravity affects light through the curvature of space-time. You might think gravity only affects mass. Well, what we learned from Einstein is that gravity is a manifestation of curved space. And when space is curved, everything that passes through it will follow the shortest path on a curved surface, which is the same effect that we see with gravity causing an orbit to form, a curved path. Light then will bend around a massive object, and because of that, one path will make you think that you're seeing a galaxy up here. The light that follows the other path will appear down here, and you end up with two images or more of the same object, the same background galaxy. This is the basics of gravitational lensing. Here is an example. Here is a galaxy that's behind this one, almost directly behind this foreground galaxy. And because of that, you see the arc there, and usually another image on the other side as well. If you get lucky and have it just perfectly lined up behind the foreground massive object, then you can get 4 images of the same background galaxy. In this case, this is a quasar, and that's the foreground galaxy right there. This is a nice simple case because it's one galaxy in the foreground. But what if you have hundreds of galaxies, thousands of galaxies, and their dark matter and their intra-cluster gas all contributing to the mass? You end up with a lens that is not optimal for imaging, but it's the only lens you got, so we're going to take it. These different colored paths represent lines where the images on that line would all be coming from the same distance behind the lens. And this is a lensing cluster, so this is kind of a map of what you'd expect the arcs, the paths that arcs could follow, if you could imagine it that way. A galaxy at one point on this blue line might match up with another image of the same galaxy on that blue line in another on the other side. So if we look at this image from James Webb and you look up close, you can see 2 galaxies there, one there and one there. You can kind of tell that they might be on the same line. They've now spectroscopically confirmed that's actually 2 images of the same background galaxy. That's kind of cool.
Why does the bright star have the hexagonal array or plus a horizontal line?
Yeah, that's a really good question. It has to do with the shape of the mirrors themselves. A round pupil of a telescope will just diffract the light uniformly around it.
I have a figure. Do you want me to put a figure of the?
Yeah, sure. Yes, I got it. That'd be great. A telescope that has a round pupil, but it has a cross in it to hold up a secondary mirror, will create stars that have a cross pattern from diffraction. And if your telescope has a hexagonal pattern to it, then it will create a cross in 3 directions. Yeah, so why don't you talk about that for a second?
Okay, yeah. So on the left-hand side, that would be the diffraction pattern if you just had a perfectly spherical mirror.
That's right there.
Yeah, with nothing in the way, that's what you get called an Airy pattern. Then if you had a hexagonal mirror, take a step over, now you have those 6-sided cross. Hubble was a circular mirror, but it had 2 struts, and so you get a nice kind of 4-sided cross.
Yeah.
JWST though has these 6-sided mirrors, so you get this 6-sided thing. But it's not just one big hexagonal mirror; it's a bunch of small ones. So it's got this special details on top. So D over there is maybe what just the mirror looks like. It's kind of a really weird diffraction pattern with all these 6-sided angles. But then E, you have to also account for the fact that there's the struts holding the secondary mirror. The light will also diffract around those. And so the difference between D and E there on the bottom is that you get an extra horizontal cross there. So there's kind of the main 6-sided cross and then a horizontal one from the struts.
It may not look pretty, but when astronomers see that, that's exciting because you're seeing the diffraction of the telescope and not scattering light from the things that we usually deal with, the atmosphere, dust on the mirror, all those other things. So the more speckly that pattern looks, the better the image generally is. And you can correct for all that, you can take it out. But that's why we have the 6-sided pattern is from the hexagonal edges of the mirrors, and then that extra little spike from the secondary support. We're used to the cross pattern from amateur telescopes because typically a Newtonian type telescope or a reflector telescope will have that problem. But if you want to take really nice pictures of planets, what do? Get a refractor or a telescope that has a corrector plate that doesn't have that support, and then what is the pattern? Then you get the cross patterns. You don't get those anymore, right? Yeah, so stars do not have tails as big as from telescopes. So here's just another example of a gravitational lens. In this case, there are 4 images there that look like spots in that galaxy. Those are 4 background images, or 4 images of something in the background. So you do have to be a little bit lucky, because you can't point this gravitational telescope anywhere you want. But if you can find out where these objects are around a galaxy cluster, you can actually make your telescope go much farther back, much farther out than you could otherwise. See much fainter things, because the gravity is going to amplify the light from those. Now this is why it's messy. This is a picture of the mass of a cluster measured through X-rays and through the lensing that tells you where the mass is located. Gravitational lensing will tell you where the mass is. And the point is, this is not a smooth, uniform, clean lens, right? This is a clumpy, distorted thing. And so you have to take into account that this is your telescope lens now. If you can deal with that kind of lens, then you can interpret the images that you see behind it. I need to talk a little bit about stars, though. We're going to talk about galaxies, we have to talk about stars briefly. And hopefully the Hertzsprung-Russell diagram is not something that's completely foreign to you. But if it is, don't worry. This axis on the graph is the luminosity of stars, or how bright they are, and the x-axis is the color or the temperature of stars. So small stars, dim red stars live down here. This is what we call the main sequence, where the stars are fusing hydrogen to helium. And up here would be the massive blue stars, giant stars. Red giants are off on this part of the diagram. If we're looking at a sequence of stars that all formed at the same time, there'd be some blue ones, some yellow ones, and some red ones. The red ones are very low mass, and they live for 1 trillion years. The luminous blue stars may only live for 1 million years.
Brown dwarfs don't figure in on this.
Brown dwarfs are not fusing hydrogen into helium in their cores, and so they don't technically fall in here, but they would be even less luminous, so they'd be way off the bottom down there. So these are the lowest mass stars up to the highest mass stars. And if you start off with a galaxy that's composed of stars of a wide range of masses, and you have some of all of these, the blue stars are going to completely dominate the light, because this star here is 1 billion times brighter than that star down there. And because it's so much brighter, even though these outnumber them, these are so much brighter, they completely dominate the light. A young galaxy that's forming stars right now is going to look blue in the optical. An old galaxy, though, how do we make it go? An old galaxy will have lost all these blue stars. So as time moves on, these stars all disappear. The galaxy is going to only have those red stars left behind, and it will become dimmer and more yellow or orange in color. So you can tell about the age of a galaxy from the predominant color of the stars. Now this is in the optical part of the spectrum, so that will be important later. If we look at a cluster of galaxies like this one, you'll see that most of these elliptical galaxies are what color?
Yeah.
They're yellowish or orangish, which means most of the stars in those galaxies are low mass stars that have been alive for a very long time, probably close to 10 or 12 billion years. Because all the blue stars are long gone. They only live for a few million years, and then they explode in supernovas. So when we see a cluster with old galaxies in them, they look red and dead, old and orange. But if you look at these arcs, a lot of them are blue. We're looking backwards in time because we're looking at galaxies that are much farther away than the cluster. and seeing those galaxies when they were just young forming stars. So these galaxies here that you see that have lots of blue stars in them, those are galaxies that are forming stars. At the light we're seeing is from when they were forming stars.
If there were more distant galaxies, they should be redshifted, shouldn't they?
They will be redshifted. Yeah, so there's two competing effects there.
You see.
Yeah, the blue light will get redshifted by the redshift. And so that what we'll end up seeing is some of the most distant galaxies will also be red as well.
Also read an article just today about some of these galaxies being very dust dense because they are younger, and that actually is artificially redshifting them as the dust is absorbing more blue spectrum.
Right. So the dust can cause things to look redder because it scatters the blue light out. Redshift can cause things to look redder, and then age can cause things to look redder. And this is a tricky problem in astronomy to sort those three things out. But I want to compare this image to this image. This is the Hubble, taken the optical wavelengths, where these are orange and a lot of the arcs are blue, young stars. When we look up close at this one from James Webb, these look kind of white. And what color are a lot of our arcs? Orange. We have now shifted to a new part of the spectrum, and the reality is none of the light in this picture has any color that you can see. So what we do typically is assign the long wavelengths red colors and the short wavelengths blue colors. Well, now the short wavelengths were what the Hubble Space Telescope had as its long wavelengths. So everything that was red is now blue. And what is now red was more red than anything Hubble could see. But now we've moved out of the stars and into the dust, where star-forming galaxies will have a lot of dust glowing in the infrared. That means a star-forming galaxy will no longer look blue in the pictures, they will now look red in the pictures. And the old galaxies now don't look red anymore, they now look white. They're not really blue, but they have an equal amount of the light across these wavelengths. And so when you see these pictures, you don't have to remember all this, but just know that the choice of wavelengths that we choose to make the colors look pretty, whatever the Hubble palette is, or, however you want to adjust the colors in your processing. For scientists, it has a specific meaning, and it allows us to say things about the composition of those galaxies or or what they're doing. It's not just about choosing pretty colors. In this case now, I don't know if you can see some of these faint little spots around here. Now we're looking at galaxies that have been redshifted, and they're still looking red, right? This particular galaxy, 13.1 billion years. That's how many years back in time it is, not light years, right? That's how many years back it is. And it was one of the most distant. Is it the most distant galaxy ever observed? At the time they were saying that, I'm not 100% sure. But this image is filled with these things, right? All these little specks in the background that just look like little tiny specks are galaxies that we're seeing 11, 12, 13 billion years after the light's left. That's very old light that's getting to our telescope now. And so this image is really full of all kinds of information, and it's just the tip of the iceberg. This is just a graphic showing how galaxies change their appearance as time goes on. A galaxy that we're looking at the time from these images here, these faint fuzzy things, are at the time when the gas clouds were just coming together for the first time and forming stars. So they've been redshifted to the point where they may look red, or they have lots of dust that make them look red. They come together, these clouds come together, they start forming stars vigorously, and sometimes they even form massive black holes that form quasars, and we end up with a lot of blue light. And then those things go away, and then they turn into elliptical galaxies that then shift more into the orange and red light again. So galaxy evolution takes place as time goes on, and by looking at galaxies at different distances, we're seeing our way through this pattern. And this is not just elliptical galaxies, this is true of spiral galaxies as well. They may start with very small, dusty, red clumps. They begin to form stars vigorously. These are space telescope images, so they're optical. We come back to the blue is young stars. And you can see how a spiral galaxy today is a mix of old and young stars, depending on this evolution. So this is just an example of how you can look at an image like this, and by looking at the colors of all those little faint fuzzy things and measuring spectra of them, we can make a map through history of a galaxy's evolution, or not a particular galaxy, but see how many galaxies evolve over time. Your turn.
Did you want this one? Or
I
we
got
using-
it there, actually.
Okay.
Okay, so that was galaxies. That's what the telescope was like built to do. I feel like that was a lot of the requirements for the instruments and stuff were all designed on how to pick up that really faint light that's been traveling throughout the universe for billions of years. But since the time where those first requirements for the telescope were defined, we found the first exoplanets. We detected the first gases in exoplanet atmospheres. So this is what I do, and this is what gets me excited. Is what James Webb can do to tell us about these exoplanets. So Joe showed the first image that ever came out of the telescope, but then a day later they came out with four other images, and one of them was a spectra, which is cool. I think it's most of what JWST will do is take spectra. So it's not going to be really beautiful images, but it's going to be information dense spectra of how bright things are at a range of different wavelengths. We can do that with an exoplanet. So I'll explain what this first spectra that came out was. It's of an exoplanet called WASP 96b. The B, lowercase b, denotes it's a planet. It's orbiting the star WASP 96. WASP stands for the Wide Angle Survey for Planets, which was it's kind of cool that in England they just strapped like a bunch of Nikon cameras together and then stared at a bunch of stars for 10 years and found hundreds of exoplanets. One of them, WASP 96b, is JWST's first exoplanet target, which is cool. So this is a transiting planet. So it's a planet that passes in front of its host star. And so if you're staring at that host star, over time, the brightness will dip as the planet blocks some of the starlight from our vantage point. You have to get lucky that you get a line just correct. But this is how we detect a lot of planets. What's cool about this as well is that you don't just detect the planet, but how the depth of this line changes as a function of wavelength is telling you how big the planet is at different colors. And that can tell you what the atmosphere is made of. Because if the atmosphere is made of water, then it's going to absorb a lot of the starlight at wavelengths associated with water, so 1.4 microns, etc. While if it was, a complete barren rock, then it would look the same at all wavelengths. And so this was the first spectrum that came out of the telescope. Here's transit depth, or amount of light blocked by the planet. So the size of the planet relative to the star, as a function of wavelength. And so it's not constant. The amount of light goes up and down as a function of wavelength, indicating that there's an atmosphere around the planet. We already knew there was an atmosphere around the planet, but what we didn't know to this high of precision was, how much water was there blocking. And so each of these bumps, there's about 5. There's a small one there, 2, 3, 4, and 5. All of that are different wavelengths of light that water is absorbing. And so we know this planet has an atmosphere rich in water, which is pretty cool. It's a big gas giant planet, so it's not like it's habitable or anything. I think it's something like 1400 Kelvin, so it's pretty hot. So not habitable or anything, but usually these big honking water features. And just to compare to what we've been doing with Hubble this whole time, Hubble's in red here, so it's the same planet looking at a similar wavelength range from the optical to the near infrared. And you can just see the error bars are much bigger. The data is just not as precise. So you get much higher precision with JWST, like order of magnitude, better precision. And it's going, just like with the galaxies, you can go all the way out into the infrared. And so you can go into this whole region that we've never even explored before. So we're going to be able to get things like new molecular species. We're going to look at, carbon species, figure out how much carbon dioxide, carbon monoxide, methane might be in these planets. So just getting started with all the stuff we'll learn from these exoplanets. Yeah, let's go into a little bit on the last couple images. Actually, I'll skip this for time's sake. This is just a zoom in into.
You guys seeing that? Let's zoom into the planetary.
Let's see, I guess we'll talk about it as it goes. Yeah, so this is one of the other images it showed was the Southern Ring Nebula. So this is a planetary nebula in the southern hemisphere, is like that, kind of like the northern hemisphere ring. This is one of the other kind of first images from the telescope. There it is. Give you a sense of scale, how kind of far you can zoom in. And this is a planetary nebula. So there's a white dwarf at the center here. This is the remnant of a dying star. This is what our sun will become eventually. And as Joe was talking about that idea of stellar evolution, as the planet dies, if it's lowish mass like our sun, it'll shed out its outer layers and to form a planetary nebula. So this is what it looks like with the telescope. And so it's all these layers that used to be part of the star. The star has flung out this gas and its outer layers onto this really beautiful nebula. I think the planetary nebulas are some of the most beautiful things in the universe. Unfortunately, their names is confusing. They have nothing to do with planets. They're, I guess back in the day when they looked at it, it looked kind of circular, so it kind of looks like a planet. But they're nebula. They're just big clouds of gas and dust with a white dwarf stellar remnant at the center of it. This is what it looks like with JWST in the near infrared, and then in the mid infrared. Now you can look a little bit more at the gas or the dust in particular, and you get basically this different view of the nebula.
Did you see that right there? It's a little edge-on spiral galaxy. Notice how it's blue in the mid-infrared from all the dust.
Yeah, so people have been saying any image that JWST takes is a deep image. You can just, galaxies are popping up. We're staring at exoplanets and then a bunch of galaxies pop up and we kind of curse the galaxies. They're getting in the way, but one person's treasure is another person's trash. And this is compared to Hubble Space Telescope. So you can get an idea of just how much more detail, bigger telescope, the different wavelengths is giving you into the structure of these gas and dust.
You can't even see that background galaxy at all.
Yeah. So you're looking with the near infrared light, you're looking through the gas and dust to see that galaxy that's kind of going to be hidden in the visible light image. Okay, do you want to talk about?
Yeah. So one of the images that they released was of the Stefan's Quintet, which has a number of interacting galaxies in it. This is the picture from the ground in the optical, and you can kind of see, at least get an idea. This one up here is not related, but these ones here are interacting. This is probably, it's not. They're just like coincidental alignment of some of these galaxies. But there's a lot, it's a pretty picture, and there's a lot going on here. So if we look at the James Webb image, you can see a lot more detail in them, right? You can see especially the dust part, these reddish parts, and in this one here, the bigger star formation is taking place in those dusty regions. Interacting galaxies are really interesting. They make pretty pictures for one, but they also trigger huge bursts of star formation. Galaxies that have maybe 100 times more star formation than the Milky Way has. And they can outshine our Milky Way by 100 to 1,000 times, especially in the infrared. These are luminous infrared galaxies, or these merging ones. But it also allows us, this is also an example of the one that they showed, because I know that there was a supermassive black hole. There's a massive black hole at the center of almost every galaxy. But when you have gas actually swirling and orbiting and falling into the black hole, you can study those black holes a lot better because you can see what's going on around them and make measurements. Our Milky Way does have a black hole at the center, but not much going on, so it makes it difficult to study. In this particular case, what James Webb is able to do by taking not just images, but images at different wavelengths to build up a spectrum, you can see the light being emitted from different elements, in this case, hydrogen, iron, molecular versus atomic hydrogen. And from that, we can determine the dynamics in the vicinity of the black hole in the center of that galaxy and study. Black holes at the centers of galaxies are really popular and cool and scary sounding things, but they actually have a lot to do with how the galaxy evolves and changes with time. There's a deep and fundamental connection between the black hole and the star formation in the rest of the galaxy, to the point that we now believe that the black hole is connected with the star formation in a way that probably the elements, that forms planets, like the elements that we're made out of, were possibly redistributed by these black holes. Black holes do not suck everything up. They're really messy eaters. They take stuff and throw it all around the galaxy. And so there's a connection between the black holes and the star. It's really, we're still studying. It's difficult to know. This is one of the most recent images from James Webb, just within the last week or so, maybe 1st of August. And this is a classic galaxy known as the cartwheel galaxy. We have cartwheels and pinwheels. It's a relatively rare form of interaction. Typically, you get galaxies interacting at angles relative to each other, and they form things that look like this, right? There's two merging galaxies. There's a highly distorted one. But if they happen to hit kind of face on, to go through the center of the galaxy face on, you can form a ring galaxy. So this is not the one in the James Webb image, but you get the idea. And as it blasts through that galaxy, it triggers star formation in the whole disk, and you end up with something that looks like this cartwheel. There's a red light in there. It's coming from that far infrared thermal emission from dust. So that's where star formation is taking place. And it's left behind this incredible rings. I'm not sure, but maybe that's the one that went through it and caused that to take place. You say when galaxies collide, what happens to the stars? So what do you think? When galaxies interact, what is the physical, what's going on? What are the chances of two stars colliding, do you think?
Zero.
It's not actually zero, but it's close. Most people would say, oh, there's got to be some. I mean, there's 100 billion, 200 billion stars. Some of them got to bump into each other, right? Well, the analogy I like to use is if our sun was the size of a 1-inch rubber bouncy ball, how far away would the nearest star be, Alpha Centauri? On that scale, a little under 1,000 miles. No, a little under 1,000 miles of Lake Texas or California. So if you got somebody in California throws one of those balls, and we throw one from Salt Lake or Orem, and they, pass each other in Nevada, what are the chances of them actually bumping into each other? Pretty small, right? But there's a lot of stars in the galaxy. There's hundreds of billions of stars. So it's possible that maybe one or two stars will collide in a collision like that, but hardly any. What's really going on is stars, this is kind of a bad animation I made, but what happens as a star passes through another galaxy, it doesn't crash into the stars, but it attracts them towards it, and those stars are attracting towards it. So basically, as a star goes through, it creates a wake behind it, and that wake pulls back on that star and creates drag, what we call dynamical friction. And that drag is what stirs up the stars and creates these amazing patterns of tails and so forth. And this optical image, you can see now, it just lights up the galaxy with star formation. It creates star formation at incredible rates because the gas collides and the stars pass through, and the gas is left behind to form new stars. As the stars do this sort of this dance where they pull stuff together and create a wake, but don't actually collide into each other. So this is the good segue into what star formation we can observe with James Webb.
So let's see. So this is my favorite image of from that first batch of images. This is from the Carina Nebula. As this is literally looking right at that gas and dust where all these stars are going to be formed. This is a star formation region where, you know, under the veil of some of this gas and dust is newly forming stars, which is really exciting. And just beautiful. I think this is the prettiest one of them all. For a reference, this is what John Herschel sketched when he looked through his telescope. It was in India when he first kind of discovered Carina Nebula. It's kind of, you know, this is our first idea of what the thing looked like. And 150 years later, now this is where we're at. If you can appreciate how much progress we've made in that time, it's kind of amazing. Just as a comparison to Hubble, again, we're looking through this gas and dust that would otherwise be blocked and invisible. We can look through it and we can look at those stars that are forming, get an idea of the actual process of star formation. So we can tie that to what's happening in these galaxies that are colliding and everything. We can actually look through the gas and dust, look at the little, you know, tiny little protostellar disk that's forming in those stars. This is a zoom in thing for the sake of time because we're running behind. If you search Carina Nebula zoom in, it's another kind of flight through the Carina Nebula, kind of like the Ring Nebula one. With music, yeah. It already has this ethereal music behind it. Okay, last few words about kind of what's next. Right now, I thought it was interesting to look at what the telescope's doing right now. Speaking of star formation, it's looking at a protostar, Ka MMS1. It's a protostar in the chameleon star formation region. This is this is, you know, declination versus ascension is kind of a map of this star formation, a map of that gas and dust. Presumably, I don't know anything about this protostar, but James Webb is looking at this right now, kind of mapping it out, looking at, you know, the gas and dust, looking at the protostar itself, and again, letting us connect what's happening here in our own galaxy to the star formation that's going to be happening in all those galaxies. It's also taking a picture. But if you're interested in what the telescope's looking at any given day, any given time, at least a week out in advance, they'll have the schedule for what it's looking at. If you just Google JWST observing schedule, it'll take you to a page. They'll have some PDFs. You can look at a schedule of the targets it's looking at, kind of maybe a short description of what the target is. Something I do every morning is look at what JWST is going to look at today. And hopefully this will continue for the next 20 years. Like I said, the fuel on the telescope was the limiting factor. That seems to have enough of it. They think maybe the limiting factor now is that the instruments weren't designed to last more than, you know, a couple decades. So it might be some, you know, moving parts, filter wheels and stuff in the instruments that might break down. So they give it about 20 years, probably more than that. But hopefully we got lots more to come. And you might see in press releases coming soon what it's been up to over the last few weeks. It's been looking at more deep fields. They spent like 13 hours at one deep field in particular, getting some nice galaxy pictures. Multiple exoplanets. In a couple of weeks, there'll be a press release about discovery of carbon dioxide for the first time on an exoplanet. So keep an eye out for that. And it's been looking at solar system objects, tons of solar system objects, looking at all of Jupiter's moons. I'm really excited to see what those pop up as. So this is a kind of a taste of what it'll look like, what Jupiter looks like through JWST. It kind of, I don't know, it's not, you have to kind of adjust your expectations a little bit for what the infrared planets look like. It'll look a little bit different than the beautiful pictures we're familiar with from Voyager or from your backyard even. But there's going to be a lot of science, like Europa could be shooting off these geysers. Same with Enceladus, moon of Saturn. James Webb will be really good at detecting some of those geysers and stuff. That's maybe something I'm excited for. But keep an eye out for these things. If you want to mess around with any of this data, federal government requires that all of this eventually becomes public. So all the data after a year it's taken will become public. But a lot of it already is public. So if you want to download some FITS files, even some PNGs of some of this data, you can go to MAST. That's the Mikulski Archive for Space Telescope. .stsci.edu, and you can search whatever target you want, and whether it's Hubble or JWST or a bunch of other telescopes, you can download the data there. So if you want to play around with some of these images, you can stack them and color code them yourself. You could do that. We're over on time, so you can ask me about what I'll be using
Pretty
JWST
easy
for.
going with the time in this group. so
Okay,
we can
okay,
take a couple minutes.
okay. Question, yeah.
This kind of just related to it. About 20 years ago, there was some Mexican PhD who developed a transfer propulsion system. It was supposed to get us to like 3/4 the speed of light. And NASA, what's it called again? And secondly, what's happened?
I don't know. I'm not familiar with.
Apparently not much, because I haven't heard.
I remember there was the EM drive thing that
Yeah,
people thought
EM
was.
drive.
Yeah, so last I heard about that one, that was one that like you shoot some microwaves at this conical metal thing and it produced an anomalous thrust. Last I heard was that they tested it, couldn't reproduce it, and that it was like something to do with like the power cable. It was the magnetic field was interacting with the power cables or something. So that seemed like kind of a bust, unfortunately, because there's no physical mechanism that it should produce thrust. So that was a kind of unfortunate bug.
Thank you.
But yeah. Maybe there's more to come then.
But really, if you guys like to, spend Friday nights combining images and playing with color palettes, and you can do it with Space Telescope images and with James Webb images.
I actually tried that a couple of weeks ago, and I don't remember what data I was looking at. It was a random choice, frankly. And some of the FITS files I could open, and some of the FITS files seemed to be in a format that couldn't figure out.
It's been difficult even for me to download like the data that I'm expecting to see. There's been a lot of like which calibrations have been done to the files already, what's available. So there's a lot that they're still working on with the pipelines, I think, and stuff where like you get these bunch of FITS files for the different filters, but they're not aligned yet. So there's a lot of stuff that's pretty raw right now. And there's a whole learning curve of like what files you actually want, which are reference files. And I downloaded 3,000 images of a blank detector the other day, and it took me a while to figure that out. So
it's getting way into the weeds, but the way these infrared detectors work is they're not like a CCD camera or CMOS camera. They don't just take the image out and that's it. They actually can sample the whole array and measure multiple times without actually resetting it. And so they don't just take one image. They take a whole sequence of images of the same thing, building up slowly. So if it saturates or something, they can just stop at that point for those pixels and then keep going with the rest.
Just stack images.
So what it is, what you get, the raw image may actually have a dozen images saved in one
Not really stacked.
FITS
but-
file, and you have to know how to get the individual planes out of it and make sense of them. But of course, we would just take thousands of them, except we can't do that because the data on board James Webb, or Space Telescope for that matter, is limited, and so you have to be judicious about how often you save those data samples along the way. So it gets really complicated really quickly. But the answer is a typical FITS image from Space Telescope or James Webb infrared camera may be actually a set of images in one file, and you have to extract them. So
Is there any publicly available software that does that? Is there?
So if you can,
probably
you can get around. You can get to you have to take the calibrator or take _cal.fits. You'll get the kind of the added sample one. Or if you do like ramp.fits, it'll be this whole thing. So you get this 4-dimensional array. So you can download the Space Telescope pipeline. It's in Python. You can run the pipeline yourself with different parameters. You can get into the weeds a lot if you're interested.
Do you know how many ground stations there are picking up data from?
So it's far enough away that it's the DSN stuff. So you get Goldstone, Canberra, and Madrid, but they each have different telescopes. The three main things.
Or three main radio dishes.
We're a little bit worried actually because the SLS is also going to use the Space Launch System for Artemis 1 is also going to use deep space the Deep Space Network. So there's not going to be enough bandwidth. So James Webb's going to have to stop observing for a little bit to save bandwidth for the human spaceflight stuff. So there's some astronomers who are bitter.
Daggum astronauts.
Yeah.
I read about Giant Magellan down in Chile that they're building, and how's that going to compare with far as images and pixels and stuff compared to web?
Yeah, so it's going to be bigger. That's what, 24 meters or something. If you go down the University of Arizona campus and you can go to the mirror lab and you can see these big 8-meter mirrors that are being ground underneath the football stadium. You can go take a tour. It's pretty cool. That's where I did my grad school. GMT is going to be like 7 of those strapped together. So they have mirrors. Some of them are being shipped down to Chile. Those will be, first flight's going to be, hopefully, it's still several years away. Telescope's going to be much bigger, so you get better spatial resolution from the ground if you can correct for the atmosphere. But shorter wavelengths. So you can't go to the infrared because the Earth's atmosphere will get in the way. Where James Webb's always going to win now is sensitivity. You can always get the dimmest stuff if you're.
So you can't compare them? They're both going to.
They're going to be pretty complementary. I think there's going to be some things you can do with one that you can't do with the other.
Mostly that they're just different wavelengths that they're optimized for. There'll be some overlap.
Yeah. Okay, one of the last things I want to mention is what I'll be using the telescope for. So there's this whole process you go through. You write some proposals. You have the science case of what you want to use the telescope for. Everybody puts in their proposals. This was November of 2020. You put in your proposals. A peer review committee looks at them, kind of figures out which ones are feasible, which ones are worth doing. So I was lucky enough I submitted 4. I got 2 of them selected. So one of them was to look at an exoplanet. This is WASP 178b, again, one of those big hot Jupiters. This one's even hotter than the last one. This is 2,500 Kelvin. I think the whole atmosphere, not only it doesn't even have any clouds of iron or anything. Everything is gaseous and even ionized. Super hot, my favorite type of planet. But these planets are cool because you can measure all the iron, all the silicon, all the titanium that's in the planet because it's all gaseous. It's not sequestered deep down. Hasn't rained out. And so you can get a really good idea of how the planet formed because you can measure the things that came into the planet as ice, the things that came into the planet as gas, the things that came into the planet as rock. And you can figure out kind of how the planet formation process works with these planets. At least that's the idea. So we'll try it out. So we're going to try and detect carbon species to get a carbon to oxygen ratio plus some silicon species so we can get a whole chemical inventory of this planet. So stuff we couldn't have done before because we can't look far enough into the infrared. For other ones, somebody mentioned brown dwarfs. I love brown dwarfs. Some people call them failed stars, which is kind of too bad for the brown dwarfs. But they're really interesting objects in and of themselves because they're really good analogs for planets because they're really high signal to noise. They're kind of just isolated. You can just stare at them for as long as you want, build up your signals to noise, and get a really good analogy for what a planetary atmosphere looks like because they can be similar temperatures. They can be, 1,000 Kelvin or something, similar to some of the hot Jupiters we were talking about before. So we're going to look at 2 of these brown dwarfs, and get 1 to 28 micron spectra of these. Mind-blowing the amount of data we'll get. This huge wavelength range at the highest possible resolution, spectral resolution with the telescope. And so the analogy I always say is it's going to be 30 times the precision that we've done before, at 20 times the spectral resolution we've done before, at twice the wavelength coverage we've ever done before of these objects. So whenever I say, it's going to be transformational, this telescope, it's like by orders of magnitude. It's not like a small step forward. This is kind of things we've really never done before. So I'm excited about that. And then, so there's going to be tons of other stuff this telescope does, looking at the early universe, looking at galaxies over time. This is what we've talked about. That's what Joe talked about. Looking in our own galaxy at these beautiful nebulae to try and look at star formation, how it's occurring by looking through this gas and dust, looking at these star formation regions, and then what happens after the stars die at those planetary nebulae. So, supernova remnants and stuff like that, what happens during these spectacular stellar explosions. And then other worlds. So that's kind of what I do, is looking at these exoplanets and brown dwarfs, looking at, maybe some terrestrial planets for the first time, looking at atmospheres around small planets, stuff like that. Really exciting stuff. I'm excited. Questions? More questions? Yeah.
I heard that the telescope is actually more sensitive than they thought it was going to be. So I've heard that a lot of proposals are dialing back their exposure time.
Yeah, that's something the people at Space Telescope Science Institute they're going through all of the programs and kind of making sure that everything's still kosher, because it's a good problem to have, but it is still a problem that we have to make sure that we're not going to saturate the detector, because that's easier to do before. Everybody's optimized it to be like as close to saturation as they can get away with, and now if it's a little bit more sensitive, pushes you over saturation. So yeah, good problem to have, but that it'll open up some things, things that would have taken an hour might not only take 45 minutes or something. So
Yes, so you can do more in less time.
yeah, definitely more efficient, which is great. And that's like a combination. The instruments are more sensitive, the mirrors, the throughput's better. It's kind of a combination of all the stuff that they had margin on with their requirements, all just kind of worked out. And so they have all this kind of extra capability, which is a good problem to have.
Do you have programs here at the university where the public can come in and watch your star shows?
So like with the planetarium?
Yeah.
We do, but it's not on a fixed schedule. It's just people will contact us and we'll set something up for their group.
How big is your group?
There's anywhere from 2 people from the group up to 45 seats.
Thank you.
So yeah, if you need contact information, let me know.
Good.
Got a question.
Yeah.
We're talking about redshift. I hear like they see some redshift at 5 or 10.
Yeah.
What are the units between 2 and 1?
Yeah, so you'll get Z, right? Z is the redshift of something. Oh.
It's a ratio, it doesn't have units, yeah.
Yeah, it doesn't have units, but it's non-linear too. So a Z of like 10 is like 13.5 billion years, and Z of 11, I don't know.
Yeah, it's highly nonlinear, and it doesn't have units because it's a ratio of the wavelength to the wavelength that is in the rest frame. So like a Z of 1 is 5 billion years ago, and 2 is 10 billion years ago, and a Z of 10 is 13 billion. So it's very
I know it's
curved.
further back, but
Yeah.
it's always got me like, what's the difference?
Most of the stars in the universe formed at a redshift of about 2, which may be just a billion or so years after the Big Bang. But a redshift of 10 is like only 400 million years later. But a redshift of 1 is 5 billion years or earlier, whatever.
There's some claims of using that SMACS field that was the first light image. Some groups have gone through, looked at, and there's some claims that there's some Z of 20 galaxies in there, which you have to go and follow it up. They're using techniques that, you need spectra of to confirm and everything, but they're going to really high Zs, higher than I think they thought they were.
For reference, the cosmic microwave background comes from redshift of 1100. And it was 380,000 years after the Big Bang. Yeah.
So since Spitzer is farther into infrared, why couldn't we see this far back?
It was telescopes only got to figure out.
Oh, okay, so just
Just didn't have the sensitivity. Yeah, and the vectors were older. It just didn't have the aperture and sensitivity. And Spitzer was limited because it was a cryogenic cooling system. So it had
ran out of cooling.
yeah, so in the frozen helium, I think it was, or whatever ran out, that was over.
There's only like,
But this one is passively cooled with its
Shield,
yeah, it's not mylar, but the reflective sheets. So as long as there's fuel to keep it out there orbiting, it'll still work.
Another question, sorry, I don't want to dominate. So those lens galaxies that are stretched, we have powerful enough computers to reconstruct what they would look like visually?
Yeah. And figure out what the pattern of the mass is in the foreground. Then you can basically plug it into a computer program that will de-stretch the galaxy and put it into what it would look like. But the uncertainty is what the mass distribution is in the lens. So there's some tricks they do to that. They do all kinds of things. They They looked for flickering in quasar signals to try to get a measure of how clumpy the dark matter is in the foreground. So they can rule out certain size, objects as far as dark matter goes. Not all brown dwarfs, for example. But they see that the images themselves flickering a little bit, and the changing of the different images with time is used to make measurements of distance. So they don't want to just look at those lensing systems. They want to watch them continuously to watch how they go up and down in brightness, because that tells you about how the mass is moving around in the foreground and how far away it is and all of those.
Yeah,
They do.
I've read that the light path is not the same, and so you will see that quasar flickering happen differently, because one light path is longer than the other.
Yeah, that's the way they measure the distances, is they'll look at those multiple images of the same thing, especially quasars, and they'll watch for it to have a change. And if one of them changes brightness significantly, then they'll watch the other ones over a period of weeks or even months. And that tells you the path length difference between the two. And from that, with geometry, you can then find out how far away it is, which is a cool trick. But you have to know about what the mass distribution is, and that's the hard part. We're not sure. Yeah. James Webb, it's everything from Jupiter to the most distant galaxies in the observable universe, and everything in between.
I can't believe the thing works.
So well.
Yeah.
So well.
I mean, I thought it was going to blow up on the launch pad.
Always a chance.
Thanks, gentlemen. That was great. Appreciate your time and sharing with us. As is usual, some of us, if anybody who wants to, will meet over at IHOP. So that's kind of it for tonight, I think. Any questions? Any questions about upcoming activities? This is the one that's in the middle is the one that's closest to us. Hopefully this one will work out this time. So
Do you want to pitch Comic-Con?
Yeah, sure. That's probably a good idea. Some of us will be doing if you attend Comic-Con, some of us will be doing there'll be 3 different panels that are put on by, well, UVAC, I suppose. It's a little more complicated than that, but Thursday of that week.